Okay, so this is our group members, which is I'm Muhammad Ifan bin Yamain, Muhammad Naim bin Osman, Adi Luqman bin Idris, Andrew Pohemi, and Muhammad Ismukri bin Abdul Azim. First things first is what we I share is problem water in digital age. So the first one is million of gallon of water, pure water are used daily. So semiconductor chips are built at a microscopic scale. Even the tiniest particle of dust or a mineral ion can ruin a chip. Therefore, at a various stage, especially for cleaning silicon, water and etching precise circuit patterns, an extremely pure form of water, known as ultra pure water, is essential. Ultra pure water is so pure that it is a highly aggressive solvent. Producing it from municipal water requires extensive and energy-intensive filtration and deionization process. The next is generation of complex wastewater. Create a stream of highly complex and contaminated wastewater. After the ultra pure water is used for cleaning and etching, it doesn't just get dirty, it becomes a toxic cocktail. This wastewater can contain heavy metal, acid and solvent, fluorides and other chemicals. This highly complex mixture is very difficult and expensive to treat before it can be safely discharged or recycled. So the summary statement is semiconductor fabs are incredibly water intensive. This sentence drives the point home. A single large semiconductor fabrication plant can use 2 to 4 million gallons of ultra pure water per day, an amount comparable to the water consumption of a small city. This creates a significant strain on local water resources, especially in regions prone to drought like Taiwan, Arizona, and the others. So that's all from me. Next to the next presenter.
The result of the fabrication process is a complex and highly variable chemical cocktail. This isn't just dirty water, it's a concentrated stream of hazardous waste that possess significant treatment and environmental challenges. First, we have heavy metal like copper, lead, and tin. These are released from the wafer during plating and etching process. If released, they are toxic and aquatic life and can persist in the environment for decades. Next are toxic and iron. Most notable fluoride from glass and silicon etching. Fluoride is difficult to remove and can be harmful and even at low concentration, requiring specialized precipitation method. The cocktail also includes strong acid and alkalis such as sulfuric acid and ammonia, used for cleaning and etching. These are corrosive and can drastically alter the pH of the wastewater, making it hostile to biological life and complicating treatment. And we can forget organic solvent like isopropyl alcohol used for precision cleaning and dyeing. That contribute to the chemical oxygen demand, starving aquatic ecosystem of oxygen and can be volatile or flammable. Individually, each of these is a problem. Combined, they create a synergetic waste stream where chemicals can interact, making the task of purification and safe disposal one of the most critical and expensive steps in the entire semiconductor manufacturing process.
Building on the need for complex treatment, we face two more critical challenges. First, the discharge limits are incredibly strict. We are not talking about parts per million. Regulations often demands parts per billion purity, To visualize that, it's like finding a single second in 2 years. Missing this target by even a small margin is not an option. This leads directly to our third challenge, cost and reliability. These treatment systems are expensive, but they must be 100% reliable. A single failure could halt billion-dollar fabrications line or worse, cause significant environmental damage. So, the pressure is immense. Achieve near perfect purity with absolute fail-safe reliability, the stakes couldn't be higher.
Okay, now about the impact of sustainable development. On the positive side, it protects water resources by preventing pollution and contamination. It also enables water recycling, meaning treated wastewater can be reused for agriculture or industry purposes. It also can drive green innovation, encouraging new technologies and sustainable business practice that reduce waste and improve efficiency. However, on the negative side, improper management can cause the ecosystem damage, especially harmful chemicals leak into natural habitat. It can also be very energy intensive. It consumes a lot of energy, and that may lead to contributing to a higher carbon emission. And also, it can also produce hazardous sludge, which must be handled safely to avoid any secondary pollution. Overall, wastewater management supports sustainability, but we must balance the environment benefit with the challenges of responsible implementation.
Now let's focus on professional ethics in engineering. Every design decision carries ethical weight. Our responsibility is to consider the long-term social impact, not just cost or efficiency. The core principle is clear. Consider long-term social impact, not only cost-effectiveness. This means advocating for the best available technology, not simply the cheapest option. It means designing for safety, redundancy, and transparency. And most importantly, it means being a guardian of public health and the environment. In essence, ethics guides us to balance practicality with responsibility, ensuring that our innovation truly benefits society and the planet.
In conclusion, treating semiconductor wastewater lies at the intersection of engineering innovation, sustainable responsibility, and professional ethics. By mastering this challenge, we not only solve a technical problem but also help build a sustainable digital future. We are Thank you for watching. We are from Group 3 BLR12. Don't forget to subscribe and give a like to this video. Thanks.